Let's start with the foundational idea behind this entire book. Many applications today are data-intensive, as opposed to compute-intensive. What's the difference? In a compute-intensive application like rendering 3D graphics, running physics simulations, or training machine learning models, raw CPU power is the bottleneck. More processing power directly equals better performance. But in most applications you'll build in your career, CPU is not the problem. The real challenges are the amount of data you're managing, the complexity of that data, and the speed at which it's changing. That's what data-intensive means. And here's what's remarkable: the tools that solve these data challenges have been so thoroughly standardized that they barely register as choices anymore. A data-intensive application is typically built from a small set of standard building blocks. Databases so that the application, or another application, can store data and find it again later. Caches to remember the result of expensive operations so that reads can be served faster the second time. Search indexes so that users can search data by keyword, or filter it in various ways. Stream processors to send messages between processes asynchronously, so that work can happen in the background without blocking the user. Batch processors to periodically crunch through large accumulated datasets, producing reports, recommendations, aggregations. If that list sounds painfully obvious, that's exactly the point. These data systems are such a successful abstraction that most engineers use them every day without thinking about them as choices at all. Most engineers would never dream of writing a new database engine from scratch. Databases are a perfectly good tool for the job. The abstraction works so well that the underlying complexity is invisible. But here's where the book starts to get interesting. The real world is not that simple. Different applications have different requirements. There are many different database systems, some optimized for fast writes, some for complex queries, some for flexible schemas, some for full-text search. There are various approaches to caching, multiple ways to build search indexes, different messaging systems with different guarantees. When building a real application, you still need to figure out which tools and which approaches are most appropriate for the task at hand. And increasingly, a single tool cannot meet all of an application's data storage and processing needs. So the work gets broken down into tasks that different tools each handle efficiently, and those tools are stitched together using application code. Imagine a realistic production setup. You have a primary database for persistent storage. You add Memcached or Redis as an in-memory cache to speed up reads. You connect Elasticsearch to handle full-text search. And you wire in a message queue for background jobs, sending emails, processing uploads, generating thumbnails. Your application code is the glue that keeps all of these in sync. When data changes in the database, the application code also invalidates the cache and updates the search index. The client making requests to your service has no idea any of this complexity exists. They see a single API, one service. But internally, you've created what the book calls a composite data system, a new, special-purpose data system built from smaller, general-purpose components. And this changes your role in a subtle but important way. You are now not just an application developer. You are a data system designer. The questions you're responsible for have changed. How do you ensure data remains correct and complete even when things go wrong internally? How do you provide consistently good performance even when parts of your system are degraded? How do you scale to handle an increase in load? What does a good API for your service look like? These aren't questions you can answer by reading any one tool's documentation. They require a system-level perspective. And many factors shape the answers: the skills and experience of the people on your team, legacy system constraints, delivery timelines, your organization's tolerance for risk, regulatory requirements. There is no universal answer. But there are principles, and that's what this book is about. Out of all the concerns that matter when designing data systems, this book focuses on three that come up in almost every system, at almost every scale. The first is reliability. The system should continue to work correctly, performing the right function at the desired level of performance even in the face of adversity. Adversity means hardware failing, software misbehaving, and humans making mistakes. All three happen in production. All three will happen to your system. The second is scalability. As the system grows in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. Notice the book doesn't say it should automatically scale. It says there should be reasonable ways to cope. Growth always requires deliberate architectural decisions. The third is maintainability. Over time, many different people will work on the system, maintaining current behavior, adapting it to new use cases, fixing bugs, investigating failures, adding features. All of them should be able to do that work productively. Not just the person who built it originally. Anyone who comes after. These three words reliable, scalable, maintainable get used in job postings, architecture documents, and engineering conversations constantly, often without anyone pausing to define what they actually mean. The book's position that vagueness is dangerous. These words are not decoration. They are engineering goals, and they need precise definitions before you can reason about how to achieve them. The rest of Chapter 1 defines each one carefully, with concrete metrics and concrete examples. That precision is what turns vague aspirations into designs you can actually evaluate and build.